Today we're going to look at page 6 of the Rational Function Note Pack. Starting with number 4. On number 4, we can see we have a rational function with a linear numerator and a quadratic denominator. And we're going to determine where this function in the end has positive values for f of x, or the y-coordinate is positive, and where the graph is negative. This type of function we use a lot in calculus, and we have to know quite often when a function is positive and when it's negative. So to start out determining where the functional values are positive and negative, what we have to do is find out where does the function have zeros and undefined values. So we'll start with that. So we want to find out where do I get my zeros from my function, and my zeros are where my graph would cross the actual x-axis. And we can see that the r of x function will have its x-intercepts take place, or its zeros take place, when the numerator is equal to 0. So when does the 2x plus 1 equal 0? And we can see that that would take place in solving that when x is equal to negative 1/2. So that's a 0 for our function. And we need to find those first, as well as find places where the graph is undefined. And the graph is undefined at locations that cause my denominator to turn to 0. And so in this case, I can see that x equals negative 3 is an undefined value, as well as x equals 1. So when we're looking at a function that is a rational function, and we're trying to determine where the functional values, or what type of y values, will cause my graph to be positive and what type of y values will cause my graph to be negative, we start out by finding zeros and undefined values. Now we're going to learn to make something called a sign chart. So this will allow us to figure out where the function is positive and negative without actually drawing the graph. So on my sign chart, oops, and I made a mistake here. On the sign chart, we just need a number line. And on our number line, we need to show on the number line where we have undefined values and zeros. So I need to go as low as negative 3. I'll go all the way down to negative 4, though. And really only as high as 1, but I'll scale the graph like so. So this is going up to 4 and down to negative 4. I have a 0 at negative 1/2, so I'm going to show my 0 at negative 1/2. And I have an undefined value at negative 3. I'm going to leave that as an open circle. That will help me later on to determine a couple things that we'll see in the future. I also have an undefined value at 1, so I'll put an open circle there as well. If those were zeros, I would make them solid dots. Now these regions of zeros and undefined values actually split our graph up into some zones. This is a zone. Between these two values, we have a zone, another zone, and another zone. And what's significant about those zones is every single input into the r of x function that is less than negative 3 will be the same sign. All the values when I input anything that's less than negative 3 will either have all the functional values be positive y-coordinates, or they'll always be negative y-coordinates, because we don't have any more zeros that are located down that are less than negative 3. Likewise, all inputs between negative 3 and x equals negative 1/2, all the inputs in here would cause my function to either be positive or to be negative. I don't have any more zeros in between here, so all the signs of the y-coordinates will always be positive or negative for any numbers in this zone. We'll have the same characteristic in this zone, the third zone, and in the zone where x is greater than 1. So what we basically need to do is we need to pick any number within a zone, input it into the function, and determine whether that functional value is positive or negative. So I'll start with the lowest zone. And the lowest zone has x being less than negative 3. So I just have to input any number that is less than negative 3, and whatever happens sign-wise with a number in that zone will happen to every number that is less than negative 3. So I'll try negative 4. Just pick something that's a convenient value to plug in. Now the nice thing about this is I don't actually have to figure out the functional value of negative 4. I just have to determine whether the value is positive or negative. So when I input negative 4 into the r of x function, I can see that the numerator would end up being negative. It's actually going to be negative 7 if you plug it in, but it's negative. That's all that matters. And in the denominator, I have two factors. And when I plug negative 4 in here, the first factor would be negative. It's actually negative 1. And the second factor would also be negative. It would actually be negative 5. So I would have a negative number in my numerator of my fraction, and then I would have it divided by a positive number. So overall, the quotient will end up being something that is negative, which means every single number that I input that is less than negative 3 will actually give me a negative value. Now I check a number that's in the zone from negative 3 to negative 1/2, and say I pick negative 1. If I pick negative 1, which again is in this zone, my numerator, plugging in negative 1, would end up being something negative. My denominator, the first factor, would actually be a positive number, and the second factor would end up being a negative number. And when I figured out this quotient, this would end up being a positive quotient, which means every single y value between these two numbers is going to be a positive value. For the third zone, I'd plug in 0. I don't want to pick fractions if I don't have to. So pick 0. My numerator, if I input it into the 2x plus 1, will be positive. My denominator has two factors. The first factor will be something that's positive. And putting 0 into the second factor in the denominator will give me something that's negative. And when I take a positive divided by, it would end up being a negative in the denominator, I'll end up getting a negative. So all values that are between this negative 1/2 and the 1 will have y values that are negative. Got one more zone, and then I just have to make my conclusion. And lastly, I have to pick a number that is greater than 1. Say I pick 2. Plugging in 2 into the numerator will yield a positive number. Plugging in 2 into both factors of the denominator will yield positive factors, which means that the quotient of those values will end up being something positive. Now I'm ready to identify my answers for Part C and D. For Part C, I need to discuss and say what values for x cause my function or my fraction r of x to end up being positive. And I can see that that's going to happen when I have values in this zone, the second zone, and in the third zone. So I will have positive x values anytime I plug in a number that is between negative 3 and negative 1/2. Now it said positive. I can't have it actually equal 0. I want it to be a positive value. If I wanted it to be greater than or equal to 0, I would put the equality here at negative 1/2. But I want it strictly to be positive. Now we also have it positive when x is greater than 1. On the other hand, my sign chart will also let me see where I have functional values that are negative. My functional values will be negative anytime x is less than negative 3, or when x is from negative 1/2 to 1. Now, question 5 is a related question to what we had in question 4. However, it looks quite different. I can see here that I have some type of an equation, or an inequality, in which I'm trying to find what values of x will cause my left side of this inequality to be negative. Now, on a function like this, I can't multiply through and cancel out the denominators as I can when this is an equality. For an inequality, I have to handle this quite differently. I will have to add these two fractions together, make these be a single fraction on this left side, kind of identifying it to look like the fraction in number 4. So I need to make this be a single fraction, and then I have to determine when that fraction is something that is negative, because I want it to be less than 0. So we're going to do some similar things, but we have some algebra that we have to start out with on this one to begin with. So I have to get a common denominator. So I'll multiply the first fraction by x minus 1 over x minus 1. And I'll multiply the second fraction by x plus 3 over x plus 3. I'm not affecting the sense of the sign at all because all I'm doing is multiplying by 1 in a little bit funny form. Now I have a single fraction. I'm going to leave the denominator in that nice factored form. In my numerator, when I distribute, I get the 5x minus 5 and the 3x plus 9, and I'm already going to simplify that down. When I add the terms together, I'm going to end up with 8x plus 4 is less than 0. Now I can see that the numerator factors and could pull out a factor of 4, but I'm actually not terribly concerned about doing any, there's nothing that's going to simplify down by factoring the top out, so that's fine just like that. So if I'm solving an inequality and I have a rational inequality, I have to do the same technique that I used in the problem above. I need to find where the function is equal to 0 and where it's undefined. I will plop those values on my number line and make a sign chart. So I need to find where does the function equal 0. The function is equal to 0 whenever the numerator is equal to 0. And the numerator is 0 when x is equal to negative 1/2 as well, when I set 8x plus 4 equal to 0. My denominator has undefined values at negative 3 and 1. Now I would do the same thing that I did in the previous example. I would make a number line, and I have unfortunately made this example have the same zeros and undefined values of the previous one, but if there were different numbers, we would map it up the same way. I would have at negative 3, I'd put that open dot because it's where it's undefined. At 1, I'd put the open dot because it's undefined. And if we had the negative 1/2 as a 0, I have that as a solid dot because it is equal to 0 there. I have my zones. And same idea as above, I would check points. I would have checked negative 4 and plug negative 4 into here and find out what happens in this zone. If I plug negative 4 in here for an x value of negative 4, I find out that my numerator is, once again, is negative. My denominator is going to be negative times a negative, and I would get a negative quotient when I would divide all that. So every single input here is negative. I would pick a point in here and plug it into this rule. And this rule, again, will end up giving me positive values if I plug anything in between negative 3 and negative 1/2 in. I could plug 0 into this rule. If I plug in 0, I end up finding that I get all negative values between here. And likewise, plug in any number bigger than 1, and I'll find out that every single input that is greater than positive 1 will end up giving me a value that is positive. Now that's not the answer to the question yet, though, because this question asks, where is our fraction less than 0? The only answer I want is the functional values, the x values that cause the functional value to be negative. So the only answer would be the zones where I have negative responses. So my answer to this inequality is I would want x to be less than negative 3, or x would be between negative 1/2 and 1. Now say, for instance, I had changed that inequality. If I had changed that inequality so that this equation said 5 is less than x plus 3 over x minus 1 is less than or equal to 0, the answer to this question we would solve very similarly to the inequality that we have when it's strictly less than. However, at the end, when we look at the sign chart, we would know we are allowing the function to actually equal 0. So there's a slight difference in solving this inequality versus this inequality that was the original. In this case, we actually would get to include negative 1/2, this 0, as part of the solution. So this inequality would have the solution that x would have to be less than negative 3. Negative 3, remember, was an undefined value. That was a value we could not plug in place of x. So that does not make the function equal 0. It makes it undefined. So that would still be part of our solution to this inequality. However, up here, we can have the function equal 0. So we would have negative 1/2 is less than or equal to x is less than 1. 1 could not be used because it was an undefined value. So you do need to recognize that there is a difference as to whether this sign is strictly less than or equal to, or on the other hand, greater than or equal to. On question 6, this is really a question that you have worked on in the past, and I'll show real quickly what the solution is for this by showing the worked out note pack. So this is kind of a review of something you've already been given questions on and quizzed on. And so I have Dixie Packaging Company wants to have a volume for their package, for their box, and it's going to be an open top box that is at least 600 cubic inches. And we're going to have a 20-inch by 25-inch piece of cardboard, and we're going to be cutting the corners out and folding them up with tape. And we want to know what size cuts should be made for these corners that are each x by x, so that this will hold at least 600 cubic inches of material. So just like we've done in the past, we would manufacture an equation that would describe the volume of this box. When we would fold this box up, we would end up having this length of the box would be the 25 inches, get my units on there, minus 2x, and then we would have the width of this box be 20 inches minus 2x, and the height of the box would be x. And so if we were solving our inequality, we would want to determine where this graph has volumes that are at least 600 cubic inches. And so remember, we did this graphically. On this, I have the function I would have put into my grapher. I know that my domain is from 0 to 10. Did a little table of values to determine that if I make my y-coordinate go up to at least 900 cubic inches, that I can see the entire graph on my screen. And I also put into my calculator that I want the volume to be 600, so I graphed a line at y equals 600 and used the intersect feature to determine these two x-coordinates. Got 1.66 and 6.16 to be the two values I would have for that. However, I want the value of the volume to be at least that big, so I would have all values for x that are from 1.66 inches up to 6.16 inches will give me values that would be legitimate cuts that would cause my volume to be at least 600 cubic inches. Okay, so that's just really a review question. And that's it for today.